And other than that, um, yes, so regarding the formula sheet, I will provide the formula sheet, and I'll share that in the next lecture as well. Okay, sounds good? Okay, so let's start. And the syllabus that is included is till today's lecture. Um, that the numericals and like the problems all related to the until today's topic, they will be included in your midterm.
I have a question.
Yes.
Where did you post the solutions? I cannot find it on.
I think they are under quiz.
Okay.
It's an ungraded quiz, so it has the practice problems and solution in that. Okay. So I think I saw in the minute paper that someone said that it's hard to understand this. What is this impedance thing? So I'll just quickly go over this so it may make sense. Okay. So what we are trying to do in input impedance scenario, that we are drawing a equivalent circuit of antenna. Okay. And we are saying that antenna, because it has to be excited, so there is a certain impedance of the generator. This is in transmit mode. And then there are resistances that are radiation resistance, which is used to send energy to the air or the free space. And then there is a loss resistance. So that's what we have done in this input impedance scenario, that we have made the what you should say equivalent circuit. So if it's very simple actually, like this equivalent circuit, because it has just the input like the generator impedance and the load impedances. So what we have done actually, we just applied our normal KVL rule in all this scenario. What we did, we said that our current should be the input voltage VG divided by the total impedance, and that's what we are doing here. And then we are saying that this is this is our antenna impedance, because it has what you should say ZA plus JXA. And then, oh sorry, and then we calculated the power dissipations across each component because of this. So we said that our power dissipation across radiation resistance will be half Ig square RR, like that is the radiation um, resistance power dissipation. And uh, then we said that power dissipated as heat in the loss resistance is this. So in all cases, we are just doing half I square R, right? And similarly, in the generator resistance, there is some power dissipation that we have calculated. Now we said that, okay, these are the power dissipation. How we can calculate the maximum power transfer? What is the best possible scenario, right? So in the best possible scenario, we said, okay, in the best possible scenario, we may not have the reactances. So it means that we have the conjugate matching condition in which the one reactance is equal to minus of the other reactance so that they can get canceled. So that's what we have done here. In the best case scenario, we said our antenna resistance is equal to the generator resistance, and our like the what you should say reactances are negative of each other, which makes us to cancel them. So by putting this scenario, we got this. We got this loss resistance, we got this generator power dissipation, and then we have calculated the supplied power dissipation. Another thing here is, if you notice, there are three types of power dissipations in the components, right? So if I say here, so these three types of power dissipations we have across the components. Now, when we get rid of the reactants, we just left with the real components. So we are saying under conjugate matching condition, our PG is equals to PL plus PR. Means, I'll start from here 1 minute. So what I'm saying is that we are talking about conjugate matching condition in which we said that um, ZA is actually equal to, no, 1 minute. In the conjugate matching condition, we said that RR plus RL is equal to RG and X A is equal to minus XG. In other words, we are saying that RA is equal to RG, like the antenna impedance is equals to the generator impedance resistance, and the conjugate is equal to the uh, uh, conjugate of antenna is equals to the generator reactance. So in other words, we are saying ZA is equal to ZA conjugate is equals to ZG or vice versa, right? Or in this case, I did make this thing, sorry. It's just the same thing. So that's what we are trying to say. Under conjugate matching condition, that's what happened. And from the expressions, we can say that our PG is equal to PR plus PL. So the power dissipation across generator is equal to the power dissipation across radiation resistance and power dissipation across load. Oh, sorry, loss resistance. So in this scenario, which means, that we have three types of power dissipation, and under conjugate matching condition, the maximum power dissipation we have is across generator impedance. So if you see here, in this scenario, our generator impedance is Vg squared over 8 and over Rg. And let me write it here. Sorry. So our PG is our PL is and our PR is okay. And if you go down, you are saying, so these are the condition like the of the maximum power transfer or conjugate matching, because they don't have the reactances in them. So you can see that if you add them together, PL plus PR, this will become which is actually equals to this thing. So, which means we have also calculated supplied power, which I will write it again here. Power supplied was so what is the relation you find between power supplied and generator dissipation across generator impedance? Mm, Bryce, do you think that there is a relationship by looking at the expressions?
By looking at the supplied power relations?
Supply power and PG.
I'm not too sure if I understand what you're looking for what you're asking.
I'm saying that what is the relationship between PS and PG? Can you, by looking at the expressions, can you find or can you see that what could be the relation between them?
PG would, in this case, would be half of what PS is.
Yes, that's what I'm looking for. Thank you. So, as he said, that PG from the expression is looking like half of PS, right? So it means that whatever you are supplying, half of the power is dissipated as across the generator impedance, and half of the power, if it is conjugate matching, is delivered to the antenna, right? Because so we are saying that this is also a dissipation and this is also a dissipation. So it means that under conjugate matching, there are two types of decimations which are equal to PG. So it means that PS is equal to half of PG and half of PL plus PR, right? This is under conjugate matching, of course, or the maximum power transfer. Does this make sense? Louis, what do you think? Yes, yes, go ahead.
Yes. You wrote PS equals 1/2 PG, but isn't it the other way around? Isn't PS twice of PG?
Yes, 1 minute. Yes, you're right. 1 minute, 1 minute. What I'm trying to say is PG is half of PS, right? PG is half of PS, yes? right? But I'm saying that PS is equal to, you are right, it's 2 into PG, right? Yes, I should write this like that. PS is equals to 2 into PG. Or I can also write this as PS is equal to PG plus PG, right? And yes, so this should not be here, I think. Thank you. Okay. So what I'm trying to say is that PS is the combination of PG and PL plus PR. Yes, thank you. Right?
Yeah.
Yes, yes, okay. So which means that when we have a power supplied, it is the combination of PG and PL plus PR, right? And so it means that I think why I added half, that it means that I want to say that half of the power is dissipated across PG and half of the power is dissipated across PL plus PR. So everybody else got what we did? Alex?
Yeah, I understand.
Okay. So now I want to say that let's assume that our PL is 0, like our loss resistance, the antenna is lossless in case of lossless antenna, which is not happening, but still, let's say. So in that case, your PS is equal to PG plus PR, right? So, which means that still you are not getting 100% of the supplied power to the radiation resistance, right? There is still the dissipation across the internal generator resistance. So, even in the maximum power transfer scenario, your total power cannot be transferred to the antenna's radiation resistance. So in other words, you can also say that to radiate half of the available power through RR, which is radiation resistance, you must dissipate the other half as heat in generator through RG. So that is the maximum power transfer scenario. Power cannot be greater than this thing. Okay? So now here we were talking about antenna that is in the transmit mode. Okay? Now we want to see that how antenna behaves in the receive mode. Receive mode means Receive mode means that some wave is coming towards antenna and it should transmit the power towards the circuitry behind that, right? So for that case, let's see, this is our antenna. Okay, and this is our load. Here, in this case, this is called load because this is a receive configuration. And then you have an incident wave coming in. Okay. Okay. So now in this scenario, if I build a equivalent circuit, my equivalent circuit will be there are two types of the impedance I have, which are related to ZT, that is RT and XT. So this would be sorry. And this will be XT. And then all the others remain same. That is RL, XL, RR, or I said this was XA, like the total antenna reactance. And this is the thing that is differ here is VT. So in the transmit scenario, you have VG at the generator side. Here you have VT towards the receiving side, because when the incident wave comes in, the voltage will induce here in the arms or at the antenna terminals. So that's why here in the receive mode scenario, you have VT at the input terminals. Okay. Sounds good?
Dr. Khan, above with where it says load, is that ZR or ZL?
It's ZT. They
ZT?
said.
Okay.
Yes, sorry. So this is ZT. Yes. Okay, so we understand this diagram. Josh, what do you think? You good?
Yeah, I think I understand.
Okay, so that's good. Miguel?
Yeah, I think I understand too.
Okay, so we are saying that this is antenna equivalent circuit in receive mode. Okay, and VT is what they call it. It's a voltage induced at the terminals. Yes, so this is voltage induced at antenna terminals. Okay, and all the other things are same. This is the load impedance. Okay, so now when we are writing the power formulas, they all will remain same except our representation will be changed. Okay, so we are saying here that our, in this case, VG, so this is the transmit mode VG is equal to the receive mode induced voltage. Okay, and when you write it, it will become like, we will just replace wherever we have G, we will replace with T, and just a minute. Okay. So that will become, 1 minute. I will write it here as PT will become okay. So if you see here, 1 minute. So here we were having 3 types of power dissipations. One was what you should say PG, one was PL, and one was PR. So what we are saying, in the case of receive mode, our VG is changed to VT. But now if you think about this, like in the receive mode scenario, you have that the power that is like the voltage that is induced on the terminals, but according to analogous, what you should say, like the corresponding scenario, your all power should not be transmitted to the load. Okay, half of the power should be going towards the load. Okay, so in this scenario, if you think about this, we talk about, instead of power supplied, we said that there is power captured. But in this scenario, your PG, what do you think? Your PG should be equals to PR plus PL, which means that what I'm trying to say is that, sorry. I think this is the scenario. Which I'm trying to say is that, do you think that your PT should be equal to PR plus PL in the case of receive mode? And if it is, how are you going to justify that? You see what my question is? Nick, do you think like you understand what I'm saying? It's hard to say, no, I don't. What I'm trying to say is that, so we are saying that these are corresponding scenarios, or these are dual scenarios, right? So what I'm trying to say is we want to prove that total power that is actually induced here in the terminals, of course, will not shift here, right? It will be like some of the power will be dissipated across the terminals, and then the remaining will be going towards the load. So that's what we want to know, or we want to figure out, that what will be the power that will be dissipated across the terminals, and what will be the power that will go towards the load. So what I'm trying to do is I am writing the corresponding terms, and then we will see what is happening. Okay, so it's just that I wrote PG, what I was writing before. Yes, so it's the same as PG, and I'm just writing this like that. And similarly, PR will be and similarly your PL will be so you're actually saying that your PT is equal to PR plus PL. We will talk about that. Just keep that in mind. Then instead of power supply, you will say the power captured is PC So it's just the same thing I'm writing, which I have written before, but it's just I am replacing VG with VT here. So once we write it, we will talk about this. So what we are saying, previously it was the other way around, that we were having power supplied, dissipated across generator impedance, dissipated across loss resistance, and then radiated through the radiation resistance, right? Now we have power captured, dissipated across load loss resistance, dissipated across what we said that uh, radiation resistance, and then transferred to the load impedance. That's the difference. It's just the order that is differing now. All the other scenarios are same, okay? So still the antenna impedance is the combination of radiation resistance and the loss resistance, and your like the load resistance is still equal to them. Like still you have this scenario where you have RR plus RL is equal to RT here, but um, but it's the order that is differing. Another thing is that if you think that your RL is 0, then in this case, if your loss resistance for lossless antenna, this will go away, then your PT is equals to PR, means half power will be dissipated across R, and then it will be transferred to the T. Okay? All the other things are same, except that we have changed VG to VT. Are we good about this? Michael,
Yeah, I'm good.
Aaron,
Yeah, I think I understand it.
okay, Saad, what do you think?
Yeah, it makes sense.
Okay. So I think I have included this problems related to this in the homework, like the practice problems. So what I will want you to do today in today's minute paper, if you want me, I will put this question as well, that if you want me to do certain problems related to certain topics, mention the topic. Okay, so let's say you don't understand this input impedance topic very well, and you want me to do problems in the next lecture related to that topic. So just mention the topic that you want me to do examples on. Okay, so in that way it will be easy for me to discuss the problems that you think that I think will help many people. Okay. Okay, so I think we have some time. I will discuss one or two things before that. Okay, so we talk about that antenna transmit and antenna receive, right? And we talk about that how some power is lost somewhere and how it is transmitted to the air or how it is being received. Another scenario here is the loss vector, polarization loss vector, that when antenna captures power, if its polarization is not aligned, there will be some loss as well, right? So it totally changed the scenario of captured energy because of the polarization loss as well. So we have to consider all these factors in that how the antenna's captured power is changed. So before doing that, I just want to mention a little bit about radiation efficiency. So um, I think we have mentioned before that antenna radiation efficiency is actually the efficiency due to conduction and dielectric losses, right? We said that ECD is the efficiency, which is also called radiation efficiency, is due to conduction and dielectric losses. But it's hard to measure the conduction and dielectric losses in antenna. So like another expression we can make out of it is that your ECD is equal to RR plus RL. So means that whatever is lost in the loss resistance plus radiation resistance, they will be in denominator multiplied by the radiation resistance. So the efficiency will be, of course, between 0 to 1 if your RL is 0, like it will be ECD will be 100% for RL is equals to 0 or for lossless antenna. But other than that, that's the formula that you can use to find the radiation efficiency. Another thing is the antenna So this topic that I'm going to start, I think that will not be included in your exam, okay? Because I'm not sure whether I will be able to finish that or not. So this antenna vector effective length and equivalent areas are not included in your midterm exam. So this is antenna vector effective length and equivalent areas. Okay, so what it means that, what is vector effective length? So sometimes it happens that your antenna is very small, but its effective length is very large. Means that your antenna's electric effect is more than its physical size. Okay, so the physical size is different than its effective length in some scenarios. So that's why we think about that, or you can also say that footprint of antenna is more than its physical size. So that's why we all the time concerned with its effective length, vector effective length. So the effective length of an antenna whether it be a linear or aperture antenna. What is linear or aperture antenna? We will talk about it. It's a type. The vector effective length is a quantity that is used to determine the voltage induced on the open circuit terminals when a wave impinges on it. So it's the quantity that determines the voltage induced on the open circuit terminal and wave impedance on it or wave comes on it. So you can say that your VOC is equal to induced electric field dot vector effective length. So we are saying that VOC is the EI is the induced electric field or induced or incident electric field. And LE is the vector effective length. We will talk about that in details, though, that what it is. But I just want to introduce this as a vector effective length. So any problems that are related to vector effective length, just leave them. And in your practice problems, why I posted all of the solutions, because I wanted to, I know you cannot solve all of the problems, but if you read a statement and you think that this problem may give me trouble, you can see the solution and see how they solved it. So it will help you to understand all sorts of the, types. Okay. I think I will stop here today, and because next time I will start a new topic and I do not want to leave it in the middle. So yes, I'm going to add this question in the minute paper, that what topics you want me to cover in the problems. Other than that, if you have any questions, go ahead.
Did the review problems ever get posted yet? Like that extra
Yes.
homework? Okay.
It's not, I did not add it in the homework. I added in the quizzes.
Okay.
So it's a practice problem. Like the topic is the practice problems.
Okay.
Any other question? You're good? Okay, thank you then, guys. Let's meet next class. Be prepared, do your homework and let me know beforehand what topic you want to cover. So then we will be good. And best of luck for your exams too. Okay, bye.
Thank you.
Thank you. Have a good one.
Dr. Khan.
Thank you. Have a good one.